Hello, everyone. I'm Tabatabaee, a PhD student in Computer and Communication Sciences at EPFL in Switzerland. And today I'm presenting our work performed with my supervisor, Professor Jeanette Boudec. So let us start. Deficit round robin, or DRR, is a simple widespread packet scheduler. With deficit round robin, we have several queues or clients, and we want to share a resource or a bandwidth among them. For example, here I assume that we have 3 flows with the corresponding packets. I'm going to use a DRR to send these packets. For the blue flow, for example, I assume that I have 3 packets with the following sizes. So what the DRR does, it first allocates some quantums to each queue. Then it visits this queue in a round-robin manner. When a queue is visited and it's not empty, the value of the deficit is increased by the value of the quantum. Then it can send some packets and the value of deficit is decreased with respect to the size of the packets that were served. Whenever the deficit is smaller than the size of the head of the line packet, the service for this flow stops, and this is what we call residual deficit. The deficit is kept for the next round. For the second flow, the same thing happens. The deficit is increased by the value of the quantum. Several packets is served and the deficit is decreased accordingly. But here what is happening is that we reach the maximum residual deficit. Maximum residual deficit is simply the maximum packet size minus 1 byte. Here, assuming that the orange flow has a maximum packet size equal to 100, the maximum residual deficit is 99. If everything was in bit, here we use 1 bit. The same thing happens for the last flow. We increase the deficit, serve some packets, but what's happening here, the queue becomes empty. We serve all the packets. In that case, the deficit is set back to 0. This is one complete round in the DRR, and the server repeats actually the same thing to serve all packets. So as you can see, deficit round robin is a very simple scheduler. In fact, it has O1 complexity, and it also achieves fair queuing in the presence of the variable length packets. And today we are interested in the delay bounds for the worst cases. Delay bounds for the worst cases for DRR found by Boyer et al., where they found actually a strict service curve. We say that beta is a strict service curve for a flow if for any backlog period of duration tau of a flow, at least beta tau, beta of the duration of the interval bits is served for this flow. Why do we care about strict service curves? Because they provide proven delay bounds. And here I explain how. Assume that the red curve is a strict service curve beta for a flow. If we also know an arrival curve constraint for the flow, the blue curve, alpha, then the delay is simply the horizontal line between the arrival curve and the strict service curve, the longest horizontal line between these two curves. So what Boyer et al. Did, they assume a DRR scheduler that receives several flows as input. Flow I, flow of interest, and other flows, for example, flow J. For each flow, we know the quantum value and the maximum residual deficit. The delay bound is found under general assumption, where we assume a strict service curve for the aggregate of the flows and a strict service curve for the DRR subsystem itself. Then the strict service curve of Boyer et al. Is illustrated here, which is in fact a rate latency strict service curve with the following values. In fact, delay bounds of Boyer et al. Dominate all previous works with no assumption on the interfering traffic. Having no assumption on the interfering traffic, on one hand, means that these delay bounds are valid even when interfering traffic behaves as unexpected, behaves in an unpredictable way. However, on the other hand, these delay bounds will be pessimistic when interfering traffic is actually constrained and behaves as expected. For such cases, Sony et al. Provide a correction term to the delay bounds of the Boyer et al. These correction terms accounts for the arrival curve constraint of the interfering traffic, and in fact, significantly improves on the delay bounds of Boyer et al. However, these correction term is based on some plausible arguments that are not formally proven. In fact, our first contribution is that we show that the delay bounds of Sony et al. Are incorrect. We show this by exhibiting a simple counterexample where it's a single DRR server with 3 input flows, where we found an execution trace in which delay of a packet is strictly larger than the delay bound of Sony et al. This is a contradiction to the delay bound of Sony et al. Being a delay bound. Very well. Until now, with no assumption on the interfering traffic, we have delays of Boyer et al., delay bounds of Boyer et al., which are the best proven delay bounds of DRR in the literature. With assumption on the interfering traffic, we have delay bounds of Sony et al., which we show that it's incorrect. Now I'm going to present our next contribution, which is first an improvement of the delay bounds of Boyer et al., and then our new delay bounds that accounts for the arrival curve constraint of the interfering traffic. Let us go through that. Back to the original problem, no assumption on the interfering traffic, same assumption as Boyer et al. This is our novel strict service curve for DRR. This is a strict service curve that improves on the delay bounds of the Boyer et al. So the good news is this strict service curve is well defined and has a closed form. However, as you observe, it has a complicated expression, which is a problem that I'm going to address further in my presentation, but first, let me illustrate it. Then, for a single example, the blue curve is our new strict service curve for DRR, which is actually a non-convex one. Then, if we know an arrival curve for the flow of interest, valid delay bound can be obtained for the flow of interest by finding the horizontal deviation between the arrival curve and our new strict service curves. Now, let us address the problem that this strict service curve is complicated. In fact, any lower bound to this blue curve, to our new strict service curve, is also a valid strict service curve and can be used to derive valid delay bounds, but the results would be less good. Being interested in rate latency strict service curve, as they are very simple and easy to use, we have found 2 rate latency strict service curve for DRR. The red curve, the rate latency with the maximum rate, and the green curve, the rate latency with the minimum latency. You cannot find any other rate latency strict service curve for DRR that dominate these ones. So these are non-dominated rate latency strict service curve. We also found a more sophisticated strict service curve by taking the maximum of these 2 rate latency, which in fact is a convex closure of our non-convex strict curve, the blue curve. All these strict service curve have very simple closed forms and are easy to use. They're very tractable. Another interesting observation is that our rate latency with the maximum rate, the red curve, is actually exactly equal to the strict service curve of Boyer et al. This means our delay bounds are guaranteed to be less than or equal to those of Boyer et al. Very well. Until now, we have seen that with no assumption on the interfering traffic, our delay bounds are guaranteed to be better than those of Boyer et al. And hence all previous works. So we have found the best proven delay bounds with no assumption on the interfering traffic. Now, let us go through the problem that we know the interfering traffic behaves as expected. Specifically, they satisfy some arrival curve constraint. For such cases, we have obtained a procedure to refine strict service curves using knowledge of arrival curves of interfering traffic. Specifically, if we know a collection of strict service curve for all flows, and also a collection of arrival curves for all flows, we have a procedure, we have a mapping that provides us a better strict service curve for every flow. How do we apply that? So we start from our strict service curve that we presently that previously presented, the strict service curve with no assumption on the interfering traffic. We combine this with the arrival curve information that we know when apply our procedure once. By doing so, we find new collection of the strict service curve. For example, here for the flow of interest, we obtain the red curve, a better strict service curve for the flow of interest. Then we know a new collection of a strict service curve. We can apply yet another time our procedure using the arrival curve information. We will again improve the strict service curve for every flow. Applying our procedure once again, the strict service curve becomes stationary. So we have a procedure, we have obtained a procedure that we can start from a strict service curve with no knowledge on the interfering traffic, iteratively apply that, and take into account for the arrival curve constraint of the interfering traffic, and we will obtain an increasing sequence of the strict service curve. I like to emphasize on the fact that all these curves, all of them are valid strict service curve and hence can be used to derive valid delay bounds. There is no need to wait for convergence or any other criteria. Here is a detailed explanation of our mapping, specifically given a collection of a strict service curve, given a collection of arrival curve, we have a mapping that is defined here, which provides us a better collection of the strict service curve for all flows. We know that it's complicated. We're going to address that, but let us first see another point. As for example, for the flow of interest, we have obtained some valid strict service curve. We can also obtain some valid delay bounds. This is done by finding the horizontal deviation between the arrival curve of the flow of interest and this strict service curve. As we have increasing sequence of a strict service curve, we will obtain decreasing sequence of valid delay bounds. Again, all these delay bounds are valid, and we can pick whatever we prefer. But as you observe, these strict service curves are costly to compute. First of all, they are non-convex. Second of all, there might be some discontinuities. To address that, we have found a simpler version of our scheme that are less costly to compute. To obtain these simpler versions, first, what we do is we start from our convex strict service curve rather than non-convex one. Second, we replace nonlinear part of our mapping with a concave expression. By doing so, we obtain convex strict service curve that are simple to compute. And let me illustrate this. So in the right here, these are the strict service curve that we have found for the flow of interest using our main scheme. For the same flow as before, the left figure show one simple strict service curve that we would found for a flow of interest using one simpler version of our scheme. As you observe, these strict service curves are convex, hence continuous, and they're easy to use. I'd like to again remind you that every curve here is a valid strict service curve, hence gives a valid delay bounds, and there is no need to wait for convergence. Very well, we have seen our new delay bounds with or without knowledge of interfering traffic. We can now go through some numerical evaluation. So we use exact same case studies as Sonny et al. The first one is an illustrative case where we have 20 flows divided in 3 classes. Each class is given a same quanta, equal quanta for every classes. These flows are actually periodic flows. Hence, we can constrain them by some token bucket arrival curves. Then we apply all methods that we have seen in this presentation to find delay bounds for these flows. For example, we first obtained the delay bounds of Ware et al., which is the black curve, the curve in the top, and we first ordered the flows by the values of Ware et al. The first observation is that our delay bounds with no assumption on the interfering traffic are always better than the delay bounds of Ware et al. The second interesting observation is that our delay bands that take into account the arrival curve constraint also improve on the delay bounds of Sony et al. We also apply our method to industrial size network where we have 8 switches, 6 input, 6 output endpoint, more than 6,000 source and destination pairs, where again we have 3 classes: critical, multimedia, and best effort. We have found the delay bounds of Boudec et al., delay bounds of Sony et al., and our delay bounds that accounts for the arrival curve constraint for all source destination pairs. Again, here we order source destination pairs by values of Boudec et al. In all of these approaches, same as Sony et al., we consider two other improvements: grouping and offset. Grouping, known also as line shaping, means when several flows arrive on the same link, we can improve the arrival curve for the aggregate of them. Offset is the improvement that that take into account the temporal separation imposed by the offset at source to obtain a better arrival curve, again for aggregate of some flows. The first observation here is that our delay bounds significantly improve on the delay bounds of Boudec et al. The second observation is that our delay bounds are practically better than even the delay bounds of Sony et al. Very well. We have seen that as of today, we have the best known delay bounds for DRR with or without knowledge of interfering traffic. And if you have any question, I'll be happy to discuss them via email. Thank you very much.